So for ideal deformation without friction or redundant work, this is the drawing stress, this is the drawing force, and this is the power. Now just like extrusion, if we include the effect of friction, right? So of course friction increases the drawing force as work has to be supplied externally to overcome friction, right? So again, without going into the details of the derivation, the drawing stress including friction is sigma d y 1 plus tan alpha by mu into this factor 1 minus af by a naught mu cot alpha. Again, right, flow stress, dicone angle, coefficient of friction, final cross sectional area of the product, initial cross sectional area of the billet material. So this is for friction, this is ideal deformation, this is for friction to overcome the frictional forces. And just to make us understand what are the different terminologies and so on, this schematic diagram is nice. It is sort of a slab analysis. This is D naught, the original dia. This is df, the final dia of the product. And here in the shaded region, we take a small differential element, whose thickness or length is dx. And this location is x, so you measure distance from any x and so on. On one side you have sigma x, on the other you have sigma x plus dx. On this surface, perpendicular to this surface, is the pressure, and of course if mu is the coefficient of friction, then the force required to overcome friction or the frictional stress is mu into p, right? Is it on this side also, on this side also. Alpha is the diangle and so forth. So all the different parameters, variables that are involved are shown here. We are not doing the homogeneous equations and so on, we are directly giving you the result. Then the redundant work. Remember, I will try to take you back to extrusion again, that here is the billet material, here is the die, the ram is pressing, the billet material pushes against the 90-degree die, pushes, nothing happens, pushes, nothing happens, pushes, nothing happens. Material is collecting here until a sizable dead metal zone is formed. Once it is formed, now the material does not hit the die, the new material comes in, hits the dead metal zone, goes to a 45-degree line and then goes in. So this much amount of work done during the formation of the dead metal zone is the redundant work, the extra work, right? The inhomogeneous deformation, the drawing stress now is sigma d, y bar 1 plus tan alpha upon mu, 1 minus af by a naught mu cot alpha. Until this it is almost the same. This additional factor 4 upon 3 root 3 alpha squared 1 minus r upon r. If this is d, this is the radius, right? This can be simplified. This is a big equation. Just to think that it is a small equation, sigma d, same for redundant work, is phi y bar 1 plus mu upon alpha ln a naught upon af. And this phi is equal to 1 plus 0.12 h upon L, right? This phi is called inhomogeneity factor, right? Because this is the inhomogeneous deformation, the redundant work, not for homogeneous deformation, for inhomogeneous deformation. So this phi is called inhomogeneity factor, and this is after simplification of this. You open it, take all the terms, see if something cancels out. So this is 1 plus 0.12 h upon L, this multiplied by the rest of it, right? And h upon L is the same thing, right? It is the dimensions of the billet and so on. So from here then, these were the three things. There was the ideal work, and then was the work against friction, and now the redundant work. So that is there. Now the die pressure, that is done, right? The three types of work that are there is done, and this is there. Die pressure along the die contact length, right? Along the die contact length. Remember, on the previous page we showed you a diagram that there is an entry angle, so the die is not directly in contact. There is an exit relief angle, so the die is not contact. But in some places the die is in direct contact with the billet material. So the pressure along the die contact length, which was called, what do you remember? The die land. That area is called the die land. So now this is P is equal to YF minus sigma. YF minus sigma. Now YF is the flow stress of the material at the die. flow stress of the material at that location, and sigma is the tensile stress in the deformation zone at a particular given dia, right? Because if it is contacting from here to here, so here the dia is different, here the dia is different. So sigma is the tensile stress in the deformation zone, in the contact zone, where the die land is directly in touch with the die at any given particular dia. So if you find sigma, we will show you later on, don't worry right now. So if you find sigma and you know the flow stress, then the difference between the flow stress and this tensile stress in the deformation zone, that is the amount of pressure that you are applying there. Okay, so these are 1, 2, 3, 4 the main equations of wire drawing. Now once the main equations are there, let us do an example. Power required excuse me, and die pressure in rod drawing. I am again and again repeating myself, but just so that it really, remember, you retain it, you remember it, you recall it, that we are doing exactly extrusion, but from the other side. Rather than pushing, we are pulling. So it is not a very difficult thing. But let us see. A round rod of annealed 302 stainless steel, it is a very popular stainless steel, is being drawn from a diameter of 10 millimeter to 8 millimeter, D0, df, at a speed of 0.5 meters per second. So the velocity is given. Assume that the frictional and redundant work together constitute 40% of the ideal work of deformation. Calculate the power required. Calculate the die pressure at the exit of the die. So you know the equation for power, you know the equation for die pressure, right? Those equations are there, and there is only this 1 or 2 pages of the mechanics of wire and rod drawing. So you can go back to these 2-3 pages where the equations are there. And as I always say, that now you pause my lecture, take blank sheets of paper and this and calculator and so on, and from your side you can go back to the lecture again, listen to it, go through it 1 time, 2 times, whatever, you can do it straight away. Write all the knowns and the unknowns, go back to the equations and see how you are doing it. Once you start listening to me again, it means you have given it your maximum try, and hopefully 80 to 90% I expect that you already have the right correct answer. For a few of you, maybe 5-10% don't have the correct answer, but they have tried their level best. And now once you have done it completely and you have checked your solution, then you are listening to the rest of the thing. So okay, so now if you are listening, then it means that we have already solved it. Now remember that there was the ideal work without friction, there was the work with friction, and there was the redundant work. So the total work is these 3, the sum of these 3. We have shown it in extrusion also. Remember, there was that graph, that there were graphs A, B, C, D, and the total one was the sum of the other 3, right? So if you have the ideal work, if you have the work against friction, and if you have the redundant inhomogeneous work, you add all of them, then you have the total work done during wire drawing or rod drawing and so on. So here they have made it very nice. You see, when they say assume that the frictional and redundant work, right? This is number 2 and number 3. Number 1 was ideal work. So assume that the frictional and redundant work together, so that sum of friction plus redundant is 40% of ideal work, right? So this is a key. This is a key. Total work is ideal plus friction plus redundant, okay? And friction plus redundant is 40% of the ideal. So you just find the ideal work, and add 40% to it, and you have the total work. Do you understand that the total work is ideal plus friction plus redundant? And here they are saying that friction plus redundant together is equal to 40% of ideal work. So find the ideal work, that is the simple equation, then add 40% to it, and you have the total. Okay, so this is what they are doing. If you know this, then the rest is there almost nothing. Okay, So I am just repeating the equations, drawing a stress ideal y ln A naught by AF. Force, the same thing with a y bar here and AF here, right, and y bar is this one, and V is the velocity, so power is force into velocity. They were asking you the power, right. Of course this is there and this is there, but this is not required, right, and so on. Okay, all that is not required, because if you just find the ideal work, then add 40% to it, so you don't have to do this, you don't have to do this. Okay, so let us see. And of course the second part of the question was the pressure, right, so this will come out to be this in the end. So this was your problem. For the solution, epsilon 1 is ln A naught by AF, right. I mean, call it epsilon 1, just find ln A naught by AF, does not matter, directly put it. But you have annealed 302 stainless steel. Annealed 302 stainless steel. To find y bar, you have to have the values of K and N. So once again, you go back to table 2.3 in the book, because this is a work that you are doing yourself. This is not a quiz, this is not an exam, the book is there. So I always want you to please don't take the values directly what I am writing here. Go back to chapter 2, go back to table 2.3, where the values of K and N for different materials are there. It is not 302 stainless steel, it is 302 stainless steel in the annealed condition, right, because this is a special heat treatment. Only 302 stainless steel will be different values. 302 stainless steel in annealed condition is a very soft material. Then you can very easily do wire drawing and so on. So for this one, the value of K is 1300 megapascal and N is 0.3. And once again, remember, sometimes these values are given as a range from here to here, some range. So if a range is given, just take the average value of the two extreme values and so on. So now you know K and N. So y bar is equal to K this. This epsilon 1 is this thing, right? Ln A naught by AF is the epsilon 1. So now you have all of this, therefore you can find the y bar, right? You have epsilon 1 from here, the values of K and N you substitute, y bar is this much. Final area of the billet, pi by 4 d square, right? dF is 8. So this is 8 millimeter, 8 into 10 raised to minus 3 meter, right? So pi by 4 d square, this is the AF. AF. Force is a stress y bar ln A naught by AF into AF directly, right? So write the value of y bar, write the value of AF, and ln A naught by AF is already this much, right? Ln A naught by AF. So you can find the force. So this is the force in mega Newton. This means 0.0175 into 10 raised to 6 Newton. Power is simply force into velocity. I am writing VF here rather than V, final velocity, velocity at the end. But this is the velocity already given, the velocity is being, so just multiply this by the velocity, keep track of the units, keep track of the units. So it is 0.00875 megawatt, or then from mega if you want to come back to kilo, 1, 2, 3, 8.75 kilowatt. If you leave it here, it is correct, but it does not look nice. So I should give you a small minus half that. Don't leave it here. Write in a nice unit of 8.75 kilowatt. Kilowatt is still a standard unit. Megawatt is still a standard unit. So don't leave it in some 10 raised to 6 watt and so on. That is correct in the number. Correct in the number. But you should always use the units that are generally used by science and physics and engineering people. So megawatt, but 0.008 megawatt, no, it doesn't look nice. 8.75 kilowatt, yes, this looks to be a reasonable value, right? Now this is only the ideal work. This is the ideal one. 40% higher, right? 40% higher, 1.4, add 40%, 1.4. So multiply this by 1.4, you have the power for all the ideal plus friction plus redundant work, right? So this is it, that initially you do everything for the ideal and then finally you just add 40%.